Deutsches Elektronensynchrotron DAISY is a high-energy physics institute located in Hamburg. For many years, this institute has been a leading science laboratory using elementary particle accelerators in its research. The Henryk Niewodniczański Institute of Nuclear Physics, Polish Academy of Sciences, has been collaborating with DAISY for about 40 years. IFJ PAN specialists have been cooperating with scientists and engineers from DAISY in the construction of the currently world's largest free-electron laser. The European free-electron laser X-FEL is an instrument of the pioneering nature used in studies of complex chemical substances, reactions at the atomic and the particle level, and in materials research. We first came to DAISY Research Center in 1992 to conduct research on synchrotron. At that time, this research was of rather pioneering character. It mainly concerned chemical elements distribution in tissues. The studies were quickly evolving. The experimental system was changing and we moved from macro systems into microsystems. We started using microbeam systems and began studies of changing oxidation states of chemical elements. We also worked on other biological materials. When first accelerators came into operation, the synchrotron of fourth generation, among others a free electron laser, there came an idea to expand the scope of this research, to conduct it at a higher level, to get the deeper insight into the structure of molecular interactions. That is why we are here. This complex facility is composed of an part responsible for accelerating the electron beam, undulators, which make the beam emit very strong X-rays, and the test stations. The accelerator part has been built using superconducting technology based on radio frequency current, which makes it possible to apply very high energies to the electron beam with the use of cavities operating at the temperature of -271 degrees Celsius. The X-FEL accelerator part comprises 100 cryomodules. Each of the cryomodules is composed of 8 superconducting cavities, which serve to accelerate the electron beam, and a single superconducting magnet for adjusting the beam shape and direction. The main task of the IFJ PAN team in this project was to test both the magnets and cavities before and after the installation in the cryomodules. The following fact illustrates well the scale of the commitment. If the task was to be carried out by a single man, it would take approximately 150 years to do the job. For this reason, a team of specialists had to be formed to execute the task: physicists, engineers and technicians from IFJ PAN. The specialists trained in mechanics, electronics, high-frequency techniques, vacuum, cryogenic and the computer science put the test stations into operation and prepared test procedures and measurement application. They conducted thousands of tests of the cavities and over 100 superconducting magnets. We are now in the premises of the DAISY Institute in Hamburg. This is the beginning of the laser under construction. The laser itself and its complex apparatus are assembled in the tunnel duct, especially for this purpose. The tunnel has a 5-meter diameter and it's about 3.5 kilometers long. Depending on the lie on the land, the tunnel is located at the depth of from 6 to 36 meters underground, despite of the fact that it has been dug in one plane. The first 2 kilometers of the laser constitute an accelerator part, where electrons are accelerated to an energy of 27 gigaelectronvolt. The second part of the laser is the photon part, in which electrons close to the speed of light are transformed into photons with the use of devices called undulators. At the very end of the tunnel there is a building with stations for performing experiments and tests. The European free electron laser is being constructed within a joint project of 11 European countries, the shareholders of the project. Poland, represented by the National Center for Nuclear Research, is one of them.
X-FEL, czyli laser na swobodnych elektronach,
X-FEL, namely the European X-ray free electron laser, is currently the world's largest facility of this kind under construction in DAISY. Poland has been a member of this undertaking laboratory facility and from the very beginning has been taking part in its construction. The Polish contribution is mostly of the in-kind form. The following three institutions participate in this project: National Center for Nuclear Research in Świerk, Institute of Nuclear Physics in Krakow IFJ PAN and Wrocław University of Science and Technology. Within our contribution, IFJ PAN has carried out the major part of the tests, which are necessary both before and after the installation of the cavities in modules. Testing this module is of crucial importance because after the modules are installed in the tunnel, it would be hard to do anything with them at that stage. The IFJ PAN group, a very large team working here in Hamburg, was responsible for testing of superconducting cavities and magnets before and after the installation and for testing the modules in the warm state and at the temperature of 2 kelvins, which is the temperature of superconducting module at work. Acquiring experience in this type of construction is absolute importance because virtually every high-energy experiment uses accelerating cavities of similar type as those used in X-FEL. This is the first such experience that the Polish team can gather, and the work of all three groups is highly acknowledged, especially the Krakow group. This is particularly important for the future, when high-energy particle experiments will be undoubtedly the only ones to be carried out. The Krakow group, with its experience in testing cavities and modules, has gained unique competence at the global scale. I'm very happy to see that the cooperation of the Polish Research Center will result in the free electron laser, which I believe should happen in more or less a year. We are currently in a hall where tests of the superconducting magnets are carried out. The tests are performed jointly by the team of DAISY employees and a group of engineers and technicians from the Institute of Nuclear Physics from Krakow. Each magnet has to pass the acceptance procedure before the actual test can be conducted. Within this procedure, the magnets undergo visual inspection and tightness and electric measurement. The tests of the magnets are performed at special stations. The first station serves to perform a warm test, i.e. test at room temperature. The second station, the cryostat, is used to carry out cold tests at the temperature below -271 Celsius. We are now in the hall where superconducting magnets for the European X-ray free electron laser are tested. We conduct these tests together with DAISY employees from the MKS4 group. The magnets undergo warm and cold tests. To carry out the cold test, the magnet must be first cooled down. This is done in special cryostats such as the one that we can see here. Inside, the magnet is cooled down to 2 Kelvin, which is about -271 degrees Celsius. The whole cycle of the magnet testing, including both warm and cold tests, take 1 week. Our task is to test 100 of such magnets. The stations are constructed in such a way that they allow the tests to be performed in 2 techniques: harmonic measurement with the use of rotation probe and a measurement with the help of stretched wire. Using a rotation probe, we can measure the properties of the magnetic field and its integral high-order harmonic poles. Thanks to the technique of a stretched wire, we can specify the location of a magnetic center and measure the torsion of the correcting magnets with respect to the main quadrupole magnet. The determination of the magnetic center is critical for future positioning the magnet in the cryomodule, as the axis of the electron beam will run through the center of the magnet. The magnet tests are controlled by computers and are carried out automatically. Where the tests are finished, the magnet is moved onto a table where it will undergo preparations for tests at the temperature of 2 kelvins. An essential component of the superconducting magnet is a current lead powering the magnet cooled down to temperature of -271 degrees of Celsius. This lead must ensure a perfect flow of current and a weak flow of warmth, so there is a stable low temperature inside the magnet. Tests of the current lead at ambient temperature comprise a measurement of resistance of 50 amp and a measurement of insulation resistance at 1000 volt. If the current lead passes the test, it can be connected to the magnet and can undergo cold test together with magnet. When the warm test is finished, the magnet is transported with the help of crane and put into the cryostat. Inside the cryostat, the magnet is plugged into the cryogenic and electric circuits. After the insulation vacuum is created, the magnet is slowly cooled down with liquid helium to the temperature of 2 Kelvin. Similar to the warm test, the cold tests are performed using two techniques with one difference. The superconducting state of the magnet makes it possible to power it with the nominal current of 50 amp. Additionally, during the measurements, a hysteresis is determined, thanks to which we can assess the behavior of the magnetic field under the influence of changing current. When the cold tests are finished, the correctness of the results in the database is verified. After warming up, lasting about 12 hours, the magnet is moved to its deposit place. At DAISY, a special hall called AMTF, Accelerating Module Test Facility, has been built for performing tests of cavities and cryomodules. It contains test stations where superconducting cavities and accelerating modules are tested. A short day-to-day briefing of DAISY and IFJ PAN specialists. The details of the ongoing works are being discussed. It is where tests of cavities and accelerating modules are carried out. The cavity tests are conducted at the room temperature and in a cooled state at the temperature of 2 Kelvin in special vertical cryostats 5 meter deep. The works are performed by a team of physicists, engineers and technicians from the Institute of Nuclear Physics Polish Academy of Sciences. We are currently in the Accelerating Module Test Facility Hall where components of X-FEL are tested. The tests are conducted by teams made up of 40 people, 25 of whom are engineers and 15 are technicians supporting the engineers. This enables us to reach a rate of the module testing amounting to 1.5 of module tested per week, as well as 12 cavities tested per week. Reaching such a rate was not a trivial task. A series of improvements and optimizations implemented by the group in cooperation with DAISY experts has resulted in speeding up the test. This means that at present we are finishing testing the serial cavities. Let me now invite you to learn more about what is going on in the hall where IFJ PAN group is working. The cavities are extremely costly and fragile devices. They are transported in special shock-absorbing crates equipped with vibration sensors, and after each transport they undergo through mechanical and electrical inspection. Cold test of cavities. In order to be tested, the cavities are installed in a special construction called an insert. In each insert, 4 cavities can be placed. The preparations for the test take 4 stages: mechanical assembly, vacuum connections, purity and tightness inspections, radio frequency electrical connections, and bandpass filters tuning. After the tightness verification, the next step is a cooling cycle to about 2 Kelvin, lasting about 1 day. All stages of both cooling and later warming are remotely controlled by the operators. At the temperature of 2 Kelvin, each cavity undergoes a test of key parameters. A measurement of the cavity Q factor dependence on its accelerating field is carried out. These measurements are conducted to check not only the cavities, but also their optimal arrangement in the cryomodules. The intensity of the electric field in the cavity is enormous. During the tests, the potential difference reaches 42 million volts per each meter of the length of the cavity between its beginning and end. At normal operation, this value amounts to over 23 megavolt per meter. Some tests are performed directly at the cavity, while the rest of them are carried out remotely. The measurement results are recorded in the database. Upon finishing the test, the cavities are transported to France to be installed in superconducting accelerating modules. Each cryomodule will have 8 cavities installed. Having finished all these operations, the cavities, which are already installed inside the modules, return from France to DAISY. Before their installation in the accelerator, the complete modules together with the cavity undergo a series of final qualification tests. The superconducting accelerating module are a fundamental element of the accelerator part of the free electron laser, and the cavities are the core. The whole laser will have 100 such modules, each containing 8 cavities. 3 stations for testing the modules have been set up in the AMTF hall. The modules will be tested after they cooling down to 2 Kelvin and using klystrons powering with 5 megavolt current at the frequency of 1.3 GHz. Before the test can begin, each module has to be adequately prepared. First, the cabling is installed, followed by a special adapter that makes it possible to connect the module with the test station. The module can now be moved to the test station located in a concrete tunnel. There the module is positioned and prepared for cooling. Within the preparation in a clean room, the system of cavities is plugged to vacuum pumps and to cryogenic pipes that cool it down. This is followed by special heat shields that are installed and insulated. Connecting the module with the test station requires over 20 kinds of special seals and over 600 screws. The purity of the cavities is checked using a mass spectrometer. Before the test begins, 8 waveguides are connected to the module. They power the cavities with the RF current produced by the klystrons. When the preparations are done, the module is cooled down to a temperature of 2 Kelvin, and after reaching the target temperature, it undergoes 2-day tests similarly to the cavities. Among other things, the cavity spectrum is studied to exclude any mechanical damages that might have occurred during the cooling. As each cavity has a different resonance frequency, they are all tuned with the use of special vector network analyzer at the identical resonance frequency of 1.3 GHz. In the next step, the cavities are tested using a klystron. In this test, each cavity is tested with respect to the upper limit of the accelerating field that it can produce. Above this limit, the cavity could lose the state of superconductivity, which could disturb its operation and result in disrupting the cryogenic condition. Before the warming up starts, the cavity are tuned to the parking positions. When the module is warmed up, access to the tunnel is opened and the module is removed from the test station and transported to its destination.
I can remember an EPAC meeting in Italy, in Genua, I think almost 8 years ago. There I met Andrzej Kotaba, and he told me that your institute will take part in X-FEL project, and that a team from your institute will be involved in all the testing of the components. And this was, I think, for me, this was the start of this. Your team was mainly involved in transfer from the prototype testing to the series testing, both for the cavities and for the car module. Your team was involved to develop also cryogenic procedures. Your team managed to write programs and process controls for automatic cool down of car modules, for instance CMTV, and was also involved in the transfer here to transfer these procedures here for AMTF and so on and so on. From my point of view, this cooperation within the X-FEL project, this is our common project. From my point of view, this worked perfectly. Your team, I think, took over all the responsibility to do this test. Your team did great work, as I said already, in the preparation of the test and in the conduction of the test, the optimization of the test. So very soon the test rates which were planned for the cavities were exceeded. And I can remember just a year ago when it seemed that the test rate for the car modules were very critical for the project. A lot of effort was needed to optimize the test, and your team did a very great job to optimize this test at the end, to shorten this test without jeopardizing the quality of the test. I can only repeat that, of course, this is a great contribution to our project. From my point of view, this is also a good example of very good cooperation within this project. So from my point of view, this is a great cooperation, and I can only thank your colleagues from Nuclear Institute for this work and also for the very good cooperation. Many thanks.